we have so far, two major concepts. Two major concepts. One is this. What does this mean again?
Difference.
Excellent. Thank you very much. And the other major concept is this. Now, we will combine these two, put them together. And what is the result? Why will I put them together? What for? Why do I need these two concepts? That's why we talked about this extensively and talked about this extensively. Okay, so let's take a look. Here's the graph of a function, f of x. And here's a point P, and point Q. We just did this a minute ago. We looked at several graphs. And obviously the slope of this line, the slope of the line PQ is the same with what we just discussed, another concept that we just discussed. What is it?
y2 minus y1 over x2 minus x1.
Excellent. The average rate of change. Thank you very much, Simone. So the average rate of change between P and Q. Between. Good. So if I have year 1, like we just did, and year 2, 2010, 2012, 2015, what you just picked a minute ago from a different graph, a different function, then I will be interested in the average rate of change between those 2 points. But what I really want to know is instantaneously. Instantaneously. What does that mean, instantaneously? I don't really care to know the average rate of change between P and Q. Here is what I want. I want the average rate of change at P. Or Q. It doesn't matter. I want instantaneously. I want the average rate of change at P. Now imagine this. I'm going to change this for a second so you can see me. I'm driving my car, let's say, to New York. And I finish my trip, and you call me and you say, tell me your average speed. And I'll say, okay, it took me 6 hours. I drove 200 miles. So I'm going to say the average speed is miles over time. I'll tell you the speed, the average speed. But now, during my trip, I start at 8 o'clock, and at 10 o'clock, you call me and say, look at your odometer and tell me the instantaneous rate of change of distance with respect to time, which is speed. Tell me, look at your odometer and tell me what is your speed now. That is the instantaneous rate of change. So I don't want to wait to determine a rate of change between 2 points. I want to be able to tell you at this instant, I drive at 61 miles an hour. And that is the instantaneous rate of change at that particular time. So that is the difference between the slope of the secant line. A secant line crosses the graph in 2 points or more, but at least 2.
Can you switch the camera?
Oh, yes, of course.
Or your...
I did something else. I clicked on sharing instead of switching the camera. Thank you. Thank you. I need you to keep me on the right track. So that's the difference between the rate of change of, or the slope of this line, which is the rate of change between 2 points, the secant line crosses the graph in at least 2 points. It can cross in more, but at least 2. And the slope of this line, so the slope of this line gives me the rate of change between these two. But the slope of this line will give me the instantaneous rate of change at that point of the function with respect to whatever it is, population with respect to time, instantaneously. Okay, how do we determine that? Putting these two together.
Are those green lines what's like supposed to signify the secant line, or were you just describing as you were talking?
That is the tangent. A tangent.
So the green lines are the tangent.
So this is the secant line. Has nothing to do with trigonometry, just says it crosses the graph in at least 2 points. And this green line is the tangent. The tangent at P, and another one, a tangent at Q. They touch the graph in only 1 point. They share only 1 point with the graph, not 2 or more, exactly 1. The slope of this line, the slope of the tangent at P, is the instantaneous rate of change at P. So how do we determine that? Instantaneous rate of change at P is the limit as x approaches, as h approaches 0 from the difference quotient, from f of x plus h minus f of x divided by h. This is the instantaneous rate of change at P. Basically, at any...
I can't see the whole formula. I'm sorry. Oh, there we go.
It's no formula. It's the limit of the difference quotient. Right? The limit of the difference quotient. So the instantaneous rate of change at P, and I have to continue because something else is very important here, at basically at any point, and something follows now that which is very important, I have to explain. At any point where the function has a unique tangent. We don't really like to write it like this.
Oh.
We like to say it.
Sorry. Oh my God.
We like to say it sophisticated. So instead of writing this, we are going to say where the function is differentiable. There is a situation in which it has a unique tangent, but it's a vertical tangent, so that is a problem. So I'm going to explain when the function is not differentiable. So I'm going to give you examples, and then we'll calculate these. Okay, so if I want to determine the slope of this line, I have to determine not the average rate of change, but in order to determine the slope of this line, which is the instantaneous rate of change, I have to determine this. I have to put the limit in front of the difference quotient. And that will give us a function. And then I will plug in the x value. Okay, it sounds very complicated. It's not. So before we choose functions and determine this and other things, I would like to explain when is the function not differentiable. When is a function not differentiable? Situation number one, when it's not continuous. If it's not continuous, the function at this point is not differentiable. Another situation will be when it's like this. It doesn't matter. It's still not continuous. This is a removable discontinuity. This is a removable discontinuity. So another situation is when it's like this. In any case in which a function is not continuous, the function is not differentiable. Here's the case number 2. If it has a corner, if it has a corner, if it has a corner, it does not have a unique tangent. It has a tangent here with a negative slope and a tangent here with a positive slope. It does not have a unique tangent. I'm going to add one more here. It's called cusp, like between two teeth. Same situation, it does not have a unique tangent. It has a positive tangent on this side, with a positive slope, I mean, and here one with a negative slope. Not a unique tangent. And the last situation is something like this. The problem here is that it has a vertical tangent. Vertical tangent have no slopes. Undefined slope. So vertical tangent. So if a function is not continuous, or it has a corner, or it has a vertical tangent, at those points, it's not differentiable. Is this function differentiable everywhere else? Yes, but not at this point. Is this function differentiable everywhere else? Yes, but not at this point. Is this function differentiable? Yes, but not at this point.
So, Professor, will we only use graphs to determine this, or is there a way to do it with some equations?
Oh, yes, with functions, with graphs. Very good question, yes. So first I'd like to determine some situation in which the function is not differentiable. So let's look on page 144. Where's my keyboard? 144, enter. Okay. So let's take a look at 25, and then we're going to go here and determine other things. But I just want to cement our conversation on when is a function not differentiable. So is the function differentiable at x0?
Yes.
Yes, of course. No corner, no cusp, no vertical tangent, and it's continuous. What about at x1?
No.
No, because it's a corner. What about at x3?
Yes.
Isn't it considered a corner?
It is a corner. It cannot be continuous. It has a tangent on this side and a different tangent on this side. So at x sub 3, it's not differentiable. What about at x sub 4 or x4?
No.
It is not continuous. Perfect. What about at x sub 5?
No.
Why?
Corner.
Corner. What about at x6?
Yes.
Yes. What about 7?
No.
No.
No, because it's not continuous. Good. So remember, what is our target? To find the instantaneous rate of change at a point. Remember my silly example? I'm driving and you want me to tell you the exact speed at that moment. If I don't have the odometer, I will not be able to tell you. Okay, so graph the function. There is no need. We graphed so many, it's okay. Draw the tangent. Oh, we can do that. I'm fine with that. So draw the lines tangent to the graph at the points with x coordinates. Good. And find f prime. So this is our notation. So finally, we can identify that the limit as h approaches 0 from the difference quotient f of x plus h minus f of x divided by h. It gives us the instantaneous rate of change for any particular x value that we want, and it has a name, and it has a notation, and here it is, f prime of x. And this is called the derivative or the first derivative. Derivative of f of x, or first derivative of f of x. Okay? So this is the definition. In the next section, we're going to learn some rules that will simplify all this, but for now, in this section, we're going to use this formal definition. This is the formal definition of the derivative of a function or first derivative of a function. F prime of x, it's a new function. It is given by the limit of the difference quotient when h approaches 0. What will give us? Again, it will give us the instantaneous rate of change for any x with the condition that that x is not where the function is discontinuous, has a corner, has a cusp, or a vertical tangent. In other words, the function is differentiable there. Okay, let's stop for a second and let me ask you questions. So do not ever, refrain yourselves from asking questions. Any questions for me? Okay, so let's look at number 11 on page 144. So f of x equals x squared minus x. It says graph the function, draw the lines tangent to the graph at the points with coordinates x equals -2, 0, and 1. Okay. So what I wanted to refresh your memory on is, first of all, we will factor out x and x minus 1 because we always want to determine the x and y intercepts. So when x is 0, I know y will be 0. So that's one intercept. And when I said y equal to 0, I get either x equals 0 or x equals 1. Is everyone okay with that? So this is already here. So we also have 1, 0. Is this okay? Does this function open upward or downward?
Upwards.
Yes, because the leading coefficient is positive. Thank you very much. Who was that?
Yeah.
Thank you. Okay, good. So I don't need to be super exact with the graph. I should find the vertex. The vertex must be right in the middle between 0 and 1, so it has to be at 1/2. Okay, so remember you used this for the previous homework. I was very pleased to see that, which is the definition of the vertex. So negative b is -1 divided by 2. So as I said, it's 1/2. It has to be exactly between these two. So if this is 1, this has to be 1/2. The axis of symmetry. So the x-intercept, and this is also the y-intercept. And now let's see how high it goes by plugging this in. So f of 1/2 will be 1/4 minus 1/2. So it will be a -1/4. So it's right here. So this is -1, so something like this. We determine the vertex. We have to graph the axis of symmetry. I have to write the function that I just graphed. Okay, so now at -2, at -2, they're asking us to draw the tangent. Fine. At that point, they're asking us to draw the tangent. Obviously, it's a negative slope. At 0, they're asking us to draw the tangent. Fine. Also a negative slope. And at 1, okay, they want us to draw the tangent. Okay. The slope of this line will give us the instantaneous rate of change of the function at -2. The slope of this line will give us the instantaneous rate of change of this function at 0. The slope of this line will give us the instantaneous rate of change of this function at 1. Okay, so we did that. And now they're asking us to find f prime. Finally, we're putting these two concepts together. So f prime of x, limit sh approaches 0 from the difference quotient. Good. So I have x squared minus x. I have to find this first. So f, like we did before, it's x plus h squared minus x plus h. Be very careful or you distribute already. I'm not going to ask you this again because you already gave it to me. And minus x and minus h. So I finally have this piece. I'm going to continue on the next page. Stop me if you have questions. Stop me if you need more time or anything.
I was still finishing copying the graph real quick. I'm sorry.
Yes.
I wanted to make sure I labeled it appropriately.
Yes, of course. Are the tangents clear?
The tangent to be -2 when it's at x and x equals 1/2? No.
So we are asked to draw the tangent to the graph of f of x when x is -2. This is the point, and I draw a tangent that touches the graph in only one point. Then at 0, I draw a tangent that touches the graph in only one point. And then at 1, I draw a tangent that has only one that shares only one point with a function.